Hello calculus folks, this is Mr. McAllen, and I'm going to be doing a series of videos to help us through the related rates process. The first thing we need to understand is how we can take any static equation and turn it into a rate-based equation. And this requires use of implicit differentiation and the chain rule. So I have a series of 5 problems. I'm going to demonstrate one for us, and then I expect you to do the other 4 problems on your own, and then I'm going to show you the solutions, and I'm going to have a pause sign that comes up so that you can have time to actually work through the problem. So on the very first problem, we'll start off with the Pythagorean theorem problem, and this is a problem that represents a triangle that you know is a right triangle, and we have x, y, and z as representing the 3 sides. And if we take a time-based derivative, just like we do with any implicit problem, we take the time-based derivative with respect to the left side of the equation and the right side of the equation. And then we use the chain rule associated with the derivative with respect to t. So the first part, we're going to get 2x times dx dt. The next part, we're going to get 2y times dy dt. And the last part, on the right side, we're going to get 2z dz dt. And this would be our rate-based equation. And there are several things we can do with this. First of all, we can cancel out the 2's. And we can also write dx dt as x dot. If you choose, we can write dy dt as y dot, and we can write dz dt as z dot. Now some people may choose not to do that. They may just want to write dx dt, dy dt, and dz dt, but this is acceptable derivative notation for a time-based derivative. So I'm going to pause the video now, and I'd like you to take the derivative of volume for where I have a volume equation that says pi r cubed. So I'd like you to find what dv dt would be if you took a time-based derivative. When you're done finding that, unpause the video and you'll see the solution. Hello, I'm back. Hopefully you had a chance to work through this single variable function, and we had to take the derivative of, since the only variable was the radius, we had to take the derivative of the radius and then make sure we use a chain rule and add the dr dt term. Next we have the volume of a cylinder, or I'm sorry, of a cone. So this would be a cone where you have a radius and you have a height. So I'd like you to find dv dt for this object. Now I'm just going to mention to you beforehand that we have 2 variables in play. We have r squared and we have h. So remember, those are variables, so we need to use the product rule. So I want you to work as a group on that, and when I come back in the video, or I unpause it, I would like you to compare your answer to what I wrote. Good luck. Here's a solution. I'd like you to talk about it, and when you're ready, begin working on the area equation of a rectangle that's over here, where I know the base and the height are going to be changing simultaneously. So now we have an area of a rectangle. We know the area is base times height. So to find the area of the rectangle, we want to take the time-based derivative of both sides. So remember, in this case, base and height are going to be changing simultaneously. So we want to make sure we also consider a product rule. I'm going to pause the video, and I want you to try finding the time-based derivative of this product. In this case, because the base and the height were being multiplied by each other, we used the product rule, where I first took the derivative of the base, and then I multiplied it by the height, and then I took the derivative of the height, and I multiplied it by the base. This is taking advantage of the product rule and doing a time-based derivative. Last problem I'd like you to try is just some arbitrary equation, x squared is equal to tan of theta. Consider x and theta are both changing simultaneously, and we'd like a time-based derivative of this equation. Well, hopefully you've started it out and you took the derivative with respect to both sides of x squared equals tan theta. And the first step on the left side would be to do 2x dx dt. And that would equal the derivative of the right side, which first I have to take the derivative of tan of theta, which is secant squared of theta, times d theta dt. And that's using the chain rule. So, if you had to find any one of these related rates, either d theta dt or dx dt, you would just solve for them algebraically with this equation. Hopefully this video, or this part of this video, has helped you understand how we can take any set of equations and turn them into time-based derivatives. So take a moment to look through all the different solutions for what we did with these 5 various equations, because I'm sure in the problems to follow you'll be using one or more of these equations to find a time-based derivative.